section 6.4, page 551, we are going to continue to work with the Taylor series. Specifically, we're going to look at the binomial series. Now, the binomial series might sound familiar to you. There's a reason for that. It's because you did the binomial series in I don't know where, okay? Maybe algebra, maybe pre-calc, maybe both. The binomial series, as you see on the page, is what happens when you multiply 1 plus x a certain fixed number of times. If you do, then it follows a pattern. Okay, the pattern is start at 1, then 1 plus x, then it becomes 1, 2, 1. I'm talking about the coefficients. Then 1, 3, 3, 1, then 1, 4, 6, 4, 1. Okay, and you've seen this several times. Now, in general, the binomial series coefficients follow this pattern. That is, this is pronounced as R choose n. Okay, and the reason, or RCN, normally it's called NCR, but your book is reversing it for a good reason. So we'll just call this, when you see this thing, this construct, we'll pronounce it as R choose n or RCN. Yeah, anyway, that's how we'll say that for now, because the book didn't tell us how to pronounce this thing. So what does this mean? This means that what you're going to do is you're going to do R factorial divided by n factorial, okay? And then divide, and where here R is bigger than n. So you're going to divide by n factorial and then divide by R minus n factorial. Now what that amounts to is that you can also write it something like this, which is equal to, when you have R factorial divided by n factorial, what you have, and R is bigger than n, what you have is something like this. You have R minus 1 times R minus 2, all the way down to R minus n plus 1. That's how far you got, right? And then the whole thing will be divided by n factorial. Okay, that's what happens when you divide R factorial by n factorial. I mean by R minus n factorial. That is, you divide out the tail end. Now, now the binomial theorem I mean, this coefficient was proven at some point or some time ago when you study this. You might or might not remember how this thing comes about. So, well, feel free to re-investigate it and refresh your memory as to how this works, or just accept it and let's move on. Your choice. Because we're not doing the binomial theorem right now, you've already been taught that. Instead, we're going to do something that is, we're going to expand the principle of the binomial coefficients, okay, to this. That is, we are going to define it as, now the normal binomial coefficients is called when R is has to be an integer, right? Otherwise, it doesn't make any sense. So let's look at what we're doing. 1 plus x to the power r, where r is some integers, and then you multiply it out, and then it becomes whatever. However, right now, we're going to do something that we're not going to care what r, even if r isn't an integer, positive integer that is. In fact, we'll accept r as a fraction or even a negative number. It doesn't matter what it is. Now, to do that, we are going to follow the Taylor series and do it by using the Taylor series expansion. Now, if we use the Taylor series expansion, then the same thing, then we come out with something like this. Okay, let's say let's say if we have a function, right, which is we have a function which is 1 plus x to the power r. And then we want to know what is the Taylor expansion of this thing. Okay, now the Taylor expansion would be, by the formula, we have to take a bunch of derivatives, right? And so we're going to calculate the derivatives, and then let's see. Yeah, we'll calculate the derivatives and then follow the now let me see. Now we are going to find the Taylor's expansion, the Taylor series for this exact function with some power r. R can be any real number, positive, negative, fractions, whatever, okay, irrational, anything. So R is any real number, and we want to calculate the Taylor series at 0, which your book calls it the Maclaurin series. Remember that. But anyway, so we're doing the Taylor series, and to do that, we follow the Taylor series formula, which means we need to calculate the nth derivative of the function f. Here's the function f. Okay, f of x equal to this thing, and we're working on just this thing. That is, we have 1 plus x. Okay, the inside doesn't change. We just, the only difference is that the r can be anything. So let's calculate this thing by hand. Okay, knowing that r is some real number, then we crank out a bunch of derivatives, as we can see here. Do the grunt work, and then we can see the f of x is that, right? F prime of x, you put the r down, and then f double prime. You see that of course the exponent keeps coming down, see, being multiplied out, and then eventually you notice a pattern. The exponents keep coming down all the way just exactly like this, right? So if you follow the formula, then the Taylor series is equal to of this particular function, then is equal to we write down the Taylor series. Okay, it equals to this expression right here. I'll choose n of and that represents the fn of 0, right? That's the derivative at 0, because yeah, so we're only doing 0 here. So the x's go to, so the x, if x is 0, then we just have these numbers left. All right, and then divide up times xn over n factorial, right? Yeah, I think so. Wait a second, do I have n factorial? N factorial is already in here. Yeah, it's just xn, sorry. Yeah, there is no n factorial because n factorial is included. All right, and as you can see, if you develop the Taylor series as 0 for a function like this, then it looks identical to the binomial expansion that we saw a little earlier. Well, it better be, because the Taylor series is unique, right? So, and once you expand it, it'll look just like the binomial expansion, and therefore they better be the same thing. So, so then that is how we write the Taylor series of this thing. And the next important question we ask is, when does this thing converge? When and if does it converge? So we apply the ratio test, and then which requires a lot of writing, but is actually very, very straightforward because you cancel out most of it. Okay, now let's see we the book apply the ratio test. You have those big long things, but you cancel it all, practically all out, so you are left with this only. Now at this point, we are to apply the ratio test, we are let n go to infinity. That is, r and x are not moving because n is the only thing we're calculating here. Okay, r is a given number, whereas x, well, x is different, but we're calculating this situation for each x. All right, so x is not changing for the purpose of applying the limit. So as you can see, when you push n go to infinity, then the whole thing the limit just approaches x. So to apply the ratio test, that means if the absolute value of x is less than 1 by the ratio test, then this thing converges. Now, what happens when so the interval convergence then is from -1 to 1. Now the behavior, what happens when x is 1 or -1? We'll worry about that later. Okay, it can be, there are various situations, but you're just gonna have to figure out when if you ever ask that question. For example, if r is bigger than or equal to 0, then the series will converge at both endpoints. If r is between 0 and -1, then the series converge at x equal to +1, diverge at x equal to -1, and when r is less than -1, the series diverges. But when that's just information that we're not going to go through right now. what we care about is that this series converges for x between -1 and 1. And that is what we got out of this exact function. So this whole time we've been working on this thing only. Okay, so the definition is this function, then it is a binomial. The Taylor series goes like this. Now remember that this definition. Now, original definition, I should mention that this is a positive number. In fact, it's a positive number that's bigger than the bottom one, which is also positive. But in our expanded definition right now, we don't care. We just blindly apply R. Even R is, say, -5. It doesn't matter. You just do this until you get to this point, and then you write your sum that way. Regardless of what R is. Okay, you just blindly do this. So it's an expanded definition of the original definition of this thing, which comes from probability, which is originally is called NCR, which are combinations. But we'll extend the definition and not care about NCR. Okay, we extend the definition to mean exactly this. And once you have this thing down, then you can expand this type of function no matter what R is. So that is that. And of course, if R is a positive integer, then this is identical to its binomial expansion. Well, it has to be because Taylor series are unique. Okay, so having said that, it converges, yes. So it converges for the absolute value less than 1. I'm looking at a definition at the bottom of the page 582. And then, yeah, and that's that. So now that we have learned about this exact type of function, we can look at it. This is called binomial series. Okay, example 6.17. You're supposed to find the binomial series and then estimate its remainder, that is the error tolerance. The error tolerance was done the Taylor theorem in the previous section, so please look that up if you need to remember exactly what it is. So that is a very straightforward plugging in numbers. So please do example 6.17 as part of your homework. Next, let's go to the page 585 and look at what your book has produced a nice chart of what we have learned so far of the various Taylor series. These are all at 0. So the book calls it Maclaurin series. That's just the Taylor series at 0. Now the Taylor series, then first originally we did 1 over 1 minus x, and then we did the e of x, right? And you can just see this in your book. And sine of x and cosine of x, and then natural log, and then tangent inverse. Tangent inverse was done earlier because the derivative of tangent is 1 over x plus x, 1 over 1 plus x squared, which as a result, we can use the geometric series to do it. That's how we did it before. And then finally, the newest one we did is the 1 plus x to the power r. Now these common series are sometimes helpful in doing homework. Then we don't have to reinvent the Taylor series for sine and just pull it out of this chart and then come up with some kind of answer. Now, as an example, let's look at example 6.18, where you're supposed to do cosine of square root of x, etc. You just plug square root of x where x used to be in the infinite series and in the Taylor series, and then the answer will come right out. So that is that's that. So please do example 6.18 as part of your homework. And next, let's look at example 6.19 on the next page. Now we're doing differentiation. Well, sometimes you can do differentiation and then and maybe come up with some kind of an answer. As the example shows, if you have square root of x, right? And then but what you need to find is 1 over square root of x. So how are you supposed to do that? Well, it just happens that the derivative of square root of x does equal to 1 over some kind of square root of x with some constant attached. So with that, you can manipulate this thing into into finding the binomial series for something. So what you're gonna do here, your book didn't write it out very much. You kept it really short. But what you're gonna do is you are going to take the derivative of one. How are you gonna take the derivative? You're gonna plug in the square root of 1 plus x with this formula right here, okay? And with r equals to 1/2. And then you are gonna take the derivative of each term in the infinite series, and then come up with this answer. Okay, that's how that is. A book probably should have written a little more, but that's the plan. If you're not sure how it's done, then yeah, don't forget to plug in this thing, infinite series, and then differentiate, and then you come up with the answer very nicely. And that is example 6.19, and please do that as your homework. Next, let's look at example 6.20, which is was trying to solve a differential equation. Now the equation has something not. This is a very simple differential equation, but the reason we want to solve it is to show you how a power series can be used to solve differential equations. So what you're going to do is that we'll write out the power series of this generic function. We don't know what it is, but we need to solve. We know this condition, okay? The derivative of y equals to y, and also the initial condition y equals to 3. Then we're going to write out the differential equation in its generic form, and then we'll take the derivative of it from the generic form. So we got this far, and then what we're going to do is apply that equation where y prime equals to y and set the two things to be equal. And at that point, you are going to be with the initial condition of y0 equals to 3, you're going to be able to figure out what each of these terms are. That is, look at the next page, where you figure out they are term by identical. So C0 equals to C1, C1 equals to C2, etc. And you line it up and solve it one at a time. See, first you figure out what C1 is, then you figure out what C2 is, and you keep going until you finally calculated what this function is. That here it is. That's the answer. And what's more, you notice that this particular Taylor series happens to be e, right? It's e to the x. It just have a 3 attached to it, so the answer is y equal to e to the 3x. Right. So that is a neat way of solving a differential equation. Let's see, and that's example 6.20. Please do that as your homework. Now you might say, what? Why do I have to go through that much work to solve a simple differential equation? I mean, that's anybody knows that y prime equal to y means is e, right? There's only one function whose derivative equals to itself, and there's some kind of e to the power x, and some maybe manipulation of it. But however, now look at the next example, example 6.21, and that is that just explains to you why we use power series to solve differential equations sometimes. Now look at this particular equation, which is called, it even has a name. It's called Airy's equation. The point is, however, the equation is tough, even though it's very, very short, right? And what's so tough about it? Now, if you look at it carefully, you notice that it has a double prime. That is, we'll have the equation involves a second derivative. Now, we have not covered how to solve second derivatives, but you can bet that it's not easy, okay? And however, the power series gives us a shortcut in solving a second derivative differential equation. What we do is do exactly the same thing we did in the previous example, is that we're going to write this thing out, the function itself, in this generic power series form, right? We'll take the derivative, we'll take the second derivative of this thing and then see what it looks like. And then use the same trick. We'll say that two things are equal, which means they are term by term identical. And then that will enable us to solve each coefficient one at a time, which will take forever because this power series is forever long, but we'll probably stop at some point when we're tired, and then we'll come up with some kind of a approximation. Let's see. So by the time you're done, then you come up with some kind of an answer. Okay, at this following page, you notice the answer is very long, and yeah, and it comes with 2 parts even. But whatever. The point is, if you go through all the grunt work of solving each one patiently, one at a time, then you get to the answer. So that shows you the power series. Using the power series can actually help you solve a differential equation that previously can't even figure out how to do it, right? So that is a pretty nice trick. So please do example 6.21 as part of your homework. Next, let's look at example 6.22, where you are supposed to integrate something that is very hard to integrate. And when something is very hard to integrate, it is called the non-elementary integral. That's what your book wants to call it. Okay, yeah, well, doesn't matter what it's called. The point is, there's no direct way to crank it out back into a nice, decent-looking function that you can look at. So to integrate it and something like that, what we can do is use the Taylor series. You just convert the function into a Taylor series, then integrate it term by term. It's a bunch of stuff added up, and then stop at some point. Okay, maybe 3. In my case, I probably stop at the 3rd term. But in any case, you stop at one point, and then you estimate the error, and then come up with a decent integration result that you normally can't do. So you can see the Taylor series is very nice. Now, example 6.22 might look familiar to you. Well, there's a reason for that. It's because we already did this problem in the previous section, right? This exact thing too, I think. And then, right? Maybe not this exact thing. Yeah, because I think in our example we stopped at 6 or something. But doesn't matter. The point is that we already did this. Okay, we've been through this, so we don't have to worry about it too much. Oh, I think in the previous example, the part we didn't do is actually taking the derivative because it was given to us. Which problem was that? Well, you remember which problem was that. It was just the previous section. So the only difference is that in that problem, we didn't have to bother taking derivatives. But being that it's e to the x, the derivative is not that tough. So we basically has already finished this problem, but you just have to remember the principle is when derivatives gets hard, sometimes you might be able to develop the Taylor series and then turn it into a long polynomial and then take the integrate it that way. And did I say derivative? I mean integrals. Okay, derivatives are almost never impossible. Integrals are often impossible. So turning it into a Taylor series, then integrate each term for a certain number of terms, it makes a decent approximation of calculating what your integral is. And that, of course, also depends on whether this thing, how good your Taylor series converges. In this case, in the case of E, I think E itself converges infinitely, no matter what x is. So this probably also converged pretty nicely. And of course, you are also supposed to calculate the error, which I think we also did. Yeah. Anyway, so did we do the error? No, I'm not quite sure. Whatever. You know, we can do error the second time. And with that, we mark the end of this section. The other examples are not particularly exciting. You just plug in numbers, which we don't care about plugging in numbers right now because we're handling the Taylor series, the infinite series. And so let's get to the homework, okay? Where we need to practice more Taylor series and binomial expansion. Now the homework, I'm not done with the homework yet. I'm only about halfway done. So, but being that I have some time to finish this to get this video, I will just simply tell you what part of the homework is. And tomorrow I'll tell you the rest of the homework. So the homework part for part 1 is we'll call this video part 1. So for homework for part 1, which is on page 596, please do problems 175, 77, 79, 81, 85, 89, 95, 197 and 201. And for problem 195, notice that there is a small error. It says 1 plus 4x. Please just do 1 plus x, okay? I have it typed right here. Replace 4x with x. The reason is because the answer at the back only gives the answer as x. It doesn't say anything about 4x. So that I think that would make sense. So that's that. Please go do your homework. And when you come back, I want to talk about some of the problems.